Hello everyone. So in this video I'm going to discuss more than 20 problem types that can be asked from the chapter Wave Optics in JEE Mains 2025. So around 1 or 2 questions can be asked from this chapter. So if you watch this video till end, I'm pretty hopeful you'll be able to answer 1 or 2 questions. Whatever number of questions which comes in JEE Mains, you'll be able to answer that. Now it's going to be a revision video, so I'm not going to derive any formula, but it is more about the application of the concept. Now first let us discuss the syllabus. So in JEE Mains 2025, we have wavefront, Huygens wave principle, right? Then law of reflection and the refraction using the Huygens principle, and then the interference. In interference, you will study YDSE, Young's double slit experiment, and then the different terms associated with YDSE, like the fringe width, angular fringe width, then coherent sources, and then the sustained interference pattern, which is possible only in case of coherent sources, then the diffraction due to a single slit, then the width of the central maxima, then the concept of polarization, what is plane polarized light, Brewster's law of Malus, then the uses of plane polarized light and the polarites. Now we're going to focus on these major areas. First is Huygens principle, so I'll discuss around 2 problem types, then interference around 2 problem types, then Young's double slit experiment around 9 problem types, then diffraction 6 problem types, and polarization 2 problem types. Now let us start with the Huygens principle. So in Huygens principle, we're going to discuss these 2 problem types. First is the different types of wavefront, and the second is the shape of the emergent wavefront. Now let us see these problem type one by one. Now if you look at the different wavefronts, so we can have a spherical wavefront, cylindrical wavefront, and planar wavefront. So spherical wavefront is being produced by the point source, whereas cylindrical wavefront is being produced by the linear source or a slit, or planar wavefront, you can say it can be produced by the extended large source, point source at a very large distance. For example, if you consider the sun is producing spherical wavefronts, but when those wavefronts reaches the earth, they appear as planar to us, right? So, and one thing you should also remember, the ray of light is always perpendicular to the wavefront. So whenever we draw a parallel beam of light, if this is the parallel beam, then the wavefront will be perpendicular to this, right? So this is the wavefront, and it will be a planar wavefront. And one more thing you have to remember, like what is how the amplitude is varying with the distance and how the intensity is varying with the distance. So if you consider spherical wavefront, amplitude is inversely proportional to r, or intensity is inversely proportional to r square. In case of cylindrical, amplitude is inversely proportional to square root of r, intensity is inversely proportional to r, and in case of a planar wavefront, amplitude as well as the intensity doesn't change, right? We can treat them as constant. Now let us see the question based on this. If the if amplitude of light at 10 meter from a small light bulb, so small light bulb can be treated as a point source, is a naught, then find the amplitude of the light at 50 meters from the same light bulb. So we know that in case of a point source, amplitude is inversely proportional to the distance from the source. So we can say A1 by A2 will be equals to R2 by R1. Now here A1 is A naught. This is A1, right? 10 meter is R1 and 50 meter is R2. So we can plug in the values. So A2 comes out to be A1 times R1 by R2. So it will be A naught times R1 is 10, R2 is 50. So this will be A naught by 5, right? So this is the answer. Now the second problem type from Huygens principle is based on the emergent wavefront, right? What is the shape of the emergent wavefront? Now if you look at the first case, if we have a prism, right, and if we incident a planar wavefront, the emergent wavefront is also planar. But if we have a converging lens and the incident wavefront is planar, then the emergent wavefront will be spherical in nature. And in case of a spherical mirror, if the incident wavefront is planar, then the reflected wavefront will be spherical. So this you have to remember, right? So there can be a qualitative question based on this. Let us see the same type of question. Light emerges out of the convex lens when a source of light kept at the focus. The shape of the wavefront of the light is, okay, let me show you the diagram. So if we have a converging lens and there is a source which is placed at the focus. And if I draw the ray diagram, so there will be rays which are coming like this. This is the incident ray, and after passing through the lens, the rays will become parallel to the principal axis because it will get converged, right? It will get converged. So what we can say, the incident wavefront will be spherical in nature, right? Why it will be spherical? Because the wavefront is always perpendicular to the rays, and the emergent wavefront will be planar in nature, right? So we have to find the shape of the wavefront of light is, so it will be nothing but plane, right? It will be planar wavefront. Now the next topic that we're going to discuss is interference. So in this topic we talk about the intensity calculation in case of coherent sources and incoherent sources. Now these are the two problem types. So interference of wave produced by coherent sources, and how to find the intensity in case of incoherent sources. So let us see the concept. So if we have given two sources, one is having intensity I1 and the other is having intensity I2, and if the sources are coherent, in that case the resultant intensity will be given as I1 plus I2 plus 2 times root of I1 I2 cos phi, where phi is the phase difference. And if I1 is equals to I2, let us say it is equals to I naught, then IR can be written as 4 times I naught cos square phi by 2, where 4 I naught is the maximum intensity, right? And if you want to find the maximum intensity, general formula, that will be root of I1 plus root of I2 whole square, and the minimum intensity will be root of I1 minus root of I2 whole square. And if we add, if we add these two, maximum and the minimum intensity, so I max plus I min will be 2 times I1 plus I2. And if we subtract these two, then it will become 4 times root I1 I2. If I call this as A and this as B, and then what is A by B? It will be I1 plus I2 upon 2 root I1 I2. So this happens in case of coherent source. But if we have incoherent source, incoherent sources, so in this case the resultant intensity is nothing but the summation of the two intensities. So this you have to remember. Now let us the question based on this concept. Now the first problem type is for how to find the intensity in case of a coherent sources. So if you look at the problem, the width of one of the two slits in YDSC is 4 times that of the other. So here you have to remember one more important concept, that the intensity of the source is directly proportional to the width of the slit. So we can say I1 is 4 times I naught and I2 is I naught, right? So that's what it is in 4:1. Now the ratio of the maximum of the ratio of the maximum and the minimum intensity in the interference pattern. So we know that I max formula, we know I minimum formula, right? So let us apply that formula. So this will be root I1 plus I2. So it will be root 4 I naught plus root I naught divided by root 4 I naught minus root I naught whole square. And if we simplify this, this comes out to be 9:1. So option 3 is the right answer. Now let us see the next question based on the same problem type. Two coherent sources of light interfere. The intensity ratio of the two sources is 1:4. For this interference pattern, if the value of I max plus I min upon I max minus I min is 2 alpha plus 1 upon beta plus 3, then what is the value of alpha plus beta? So we know the value of this is nothing but I1 plus I2 divided by 2 times root I1 I2, and we can take I1 as I naught and I2 as 4 I naught. Now let us substitute these values in this ratio. So it will be 5 I naught divided by 2 times root 4 I naught square, which will be 5 by 4. So this comes out to be 5 by 4, and it is given as 2 alpha plus 1 upon beta plus 3. So we can write 5 as 2 times 2 plus 1, and 4 can be written as 1 plus 3. So we can say alpha is 2 and beta is 1. So what is the ratio? So ratio of 2 and 1 will be 2. So option B is the right answer. Now the next problem, again based on the same concept. The two light beams have intensity I and 9I interfere to produce a fringe pattern on the screen. The phase difference between the beam is pi by 2 at P and it is pi at Q. Then the difference between the resultant intensity at P and Q. So here we have to use resultant intensity formula, which is I1 plus I2 plus 2 times root I1 I2 cos phi. Now let us apply this formula for P. So intensity at P will be I plus 9I plus 2 times root of 9I square times cos pi by 2. And we know that cos pi by 2 is 0, right? So intensity at P will become 10I. Now let us find the intensity at Q. So intensity at Q will be I plus 9I plus 2 times 3I cos pi. And cos pi is negative 1. So this comes out to be 10 minus 6I, which will be 4 times I. And we have to find the difference between the resultant intensities. So IP minus IQ comes out to be 6I. So option B is the right answer. Right, so let us see the next question. In YDSC experiment, the intensity at 2 points for a path length difference lambda by 4 and lambda by 3 is I1 and I2 respectively. So here let me tell you one more important concept, the relation between the path length difference and the phase difference. So 2 pi by lambda times delta x is nothing but the phase difference, where delta x is the path length difference and phi is the phase difference. So let me write here. So this is path length difference and this one is phase difference. So we have to find I1 plus I2 upon I0, where I0 is given as intensity produced by each one of the individual slits. Okay, so let us try to solve this. So first what we have to do, we have to use this formula to find the phase difference, right, for the corresponding path length difference. So we can say phi 1 will be 2 pi by lambda times lambda by 4, so which comes out to be pi by 2, and phi 2 comes out to be 2 pi by lambda times lambda by 3, so this will be 2 pi by 3. Now using the now again we have to use the resultant formula, resultant intensity formula, which is I1 plus I2 plus 2 times root I1 I2 cos phi. But here we have given that both the sources have the same intensity, so this formula will become 4 I naught cos square phi by 2. Now let us use this formula, no? So let us use this one. Now if we use this formula, the intensity I1 will be 4 I naught cos square pi by 4, and pi by cos pi by 4 is 1 by root 2, so this will be 1 by 2, so this comes out to be 2 I naught, and I2 comes out to be 4 I naught cos square pi by 3, and cos pi by 3 is 1 by 2, so that will become 1 by 4, so this will become I naught. So we have to find I1 plus I2 by I naught, so it will be 3 I naught upon I naught, so that will be 3, so option 3, answer will be 3. Right, so let us see the next question. Now this is the second problem type in interference, where we have to find the intensity due to incoherent sources. So two waves of intensity in ratio 1:9 cross each other at a point. The resultant intensity at the point when when the waves are incoherent. So when waves are incoherent, intensity is I1. B, when the waves are coherent, and intensity is I2, and the phase difference is 60 degrees. And we have to find the ratios of the intensities I1 and I2, which is given as 10 by x. We have to find the value of x. Right, so I told you, when for A part, we have to simply add up the intensity. So I'm taking I1 as I naught and I2 as 9 times I naught. So this will be I1 plus I1 prime, let us say I2 prime, I1 prime plus I2 prime. So this comes out to be I naught plus 9 I naught. So this will be 10 I naught. And I2 will be I1 prime plus I2 prime plus 2 times root of I1 prime I2 prime cos phi. So this formula we have to use. So this will be I plus 9I naught plus 9I naught plus 2 times, so root of 9I naught square, which will become 3I naught, then cos 60 degree, and cos 60 is 1 by 2. So the cos 60 will cancel this 2. So this will become 10 plus 3, so 13 I naught. So if we take the ratio, so I1 by I2 will be 10 by 13, which is 10 by x. So from this we can say x is nothing but 13. So 13 is the answer of this question. Now if we consider, now the next concept is YDSE, Young's double slit experiment, and in this particular concept there are 9 problem types. So first let us see the important terms that we consider in YDSE. So in YDSE there will be 2 slits. S1 and S2 are the 2 slits, and let us say the rays are coming like this. So we have a parallel planar wavefront approaching the 2 slits. The distance between the slit and the screen is capital D, and the distance between the slit is small d. So here let us see some important terms that you have to consider. So first is phase difference. So if I consider any point on the screen, let us say this point P, and its distance from the central maxima is y, and this angle is theta, then path length difference at P will be given as delta x, and it will be d tan theta, and tan theta will be y by capital D. And we can apply delta x as d tan theta only in case when both the assumptions are valid. And what are the two assumptions? So first assumption is when capital D is very large in comparison to small d, and the second assumption is that y is very small in comparison to capital D, or we can say lambda is very small in comparison to small d. Right? These are the two assumptions. And second, we have to consider fringe width. So fringe width is given as d lambda by small d. And third is angular fringe width, let us say it is alpha, and is given as lambda by d. And fourth, position of bright fringe. So position of bright fringe will be given as n d lambda by d, where n will be 1, 2, 3, 4, right? And fifth, position of dark fringe will be 2n minus 1 d lambda by 2d. Right? So these formulas we have to remember, and these formulas are applicable like fringe width, angular fringe width, position of the bright fringe, position of the dark fringe. These formulas are applicable if both the assumptions are valid. Now let us see the different problem types. So in YDSE, the width of one of the slit is 3 times the other, and the amplitude of the light coming from the slit is proportional to the slit width. So here they have clearly mentioned that the amplitude of light coming from the slit is proportional to the slit width. But usually what happens, the intensity is proportional to width, but here they have given amplitude, and we know that intensity is directly proportional to square of the amplitude, and amplitude is directly proportional to the width. So we can say intensity will be directly proportional to the square of the width, right? And one slit is 3 times the other, so we can say if I1 is I0, then I2 will be 3 square times I0, which will be 9 times I0. Find the ratio of the maximum to the minimum intensity. So I max upon I min. So it will be root I1 plus root I2 upon root I1 minus root I2 whole square. So this comes out to be 3 root I0 plus root I0 upon 3 root I0 minus root I0 whole square. So if we simplify this, this comes out to be 2 by 1 whole square, which will be 4 by 1. So 4:1 is the answer. Option 3 is the right answer. Now the next problem type is based on fringe width. So the width of the fringe is 2 millimeter. On the screen in double slit experiment for the light of wavelength 400 nanometer, the width of the fringe for the light of wavelength 600 nanometer. So here we have to do the comparison. So we know that fringe width is given as d lambda by d, and now we are changing the wavelength, keeping capital D and small d same. So we can say beta is directly proportional to lambda. So we can say beta 2 by beta 1 is equals to lambda 2 by lambda 1. Now this is lambda 2, this is lambda 1, and this is beta 1. So let us plug in the values. So beta 2 will be beta 1, which is 2 into 10 raised to power minus 3 times lambda 2 upon lambda 1. So it will be 600 divided by 400. So this comes out to be 3 millimeters. So option 3 is the right answer. Again, it is based on fringe width, this problem. So in a double slit experiment with monochromatic light, fringes are obtained on the screen placed at some distance from the plane of the slits. If the screen is moved, now we are changing the distance between the slits and the screen. So capital D is being changed by 5 into 10 raised to power minus 2. So it means delta D is 5 into 10 raised to power minus 2 meters. And the change in the fringe width is 3 into 10 raised to power minus 3 centimeter. Now this is delta B, which is 3 into 10 raised to power minus 3 centimeters. If the distance between the slits is 1 millimeter, then the wavelength of the light. So we have given small d as 1 millimeter, and we have to find the wavelength, right? So we know that beta is d lambda by small d, or we can write this as delta beta will be equals to lambda by d times delta d. Now from this we can say lambda will be d times delta beta divided by delta d. Now let us put the values. So small d is 10 raised to power minus 3. I have converted this into meters. And delta beta is 3 into 10 raised to power minus 3 times 10 raised to power minus 2, again in meters, divided by delta d, which is 5 into 10 raised to power minus 2. So let us simplify this. So this will get cancelled out. So it will be 0.6 into 10 raised to power minus 6, and we have to find answer in nanometers. So 10 raised to power minus 3 divided by 10 raised to power minus 3, which is 600 into 10 raised to power minus 9 meter. So the answer will be 600. Again, the illustration based on fringe width. In YDIC, the fringe width is 12 millimeter. If the entire arrangement is placed in water of refractive index 4 by 3, then the fringe widths become. So we have to find the answer in millimeters. So beta is given as d lambda by d. Now if we change the medium, wavelength will change. So lambda in medium is equals to lambda in say vacuum divided by the refractive index of the medium. So here the new lambda, let me call this as lambda 2, will be equals to lambda 1 divided by the refractive index 4 by 3, right? So can you see the lambda will decrease by 4 by 3. So we can say beta 2 by beta 1 is equals to lambda 2 by lambda 1. So lambda 2 by lambda 1 is 3 by 4. So beta 2 will be 3 by 4 times 12 millimeters. So that will be 3. So this comes out to be 9 millimeters. So option B is the right answer. Now let us see the next question. Again, it is based on fringe width. In a YDSC experiment, the distance between the slits varies in time as. So the distance between the slit is varying. It is a harmonic function where d naught, omega and a naught are constants. Difference between the largest fringe width and the smallest fringe width obtained over the time is given as. Okay, so we have to find beta max and beta min difference. Now beta max is what? So beta max will be d lambda by d minimum. If the distance between the slit is minimum, then beta will be maximum, because we are varying the distance between the slit. We are not changing the distance of the screen from the slit. It is not given in the question. And beta minimum will be when the distance between the slit is maximum. So d lambda upon d max. Now what is d max? So d max will be what? So if you look at this, here we have sine function and the maximum value of the sine function is plus 1. So d max will be d naught plus a naught. Similarly, the minimum value will be d naught minus a naught, because the minimum value of sine function is negative 1. So d naught minus a naught. So we can say d lambda. So the difference will be d lambda upon d naught minus a naught minus d lambda upon d naught plus a naught. So this will give us d lambda times 2a naught divided by d naught square minus a naught square. So option 2 is the right answer. Now the next problem type is based on angular fringe width, and we know the formula. So let me take it as theta only. So theta will be lambda by d, small d, not capital D, it will be small d, distance between the slits. So in YDSC, an angular width of the fringe is 0.35 degrees on the screen placed 2 meters away from the particular wavelength of 450 nanometer. The angular width of the fringe when the whole setup is immersed in a medium of refractive index 7.7 by 5 is 1 by alpha. The value of alpha is. So we know that if we keep d constant, the fringe width is directly proportional to lambda. So we can say theta 2 by theta 1 will be lambda 2 by lambda 1. And we know that lambda 2 will be lambda 1 divided by the refractive index. So lambda 2 by lambda 1 is 5 by 7. So this will be 5 by 7. So theta 2 will be 5 by 7 times 0.35, which comes out to be 0.25 degrees, and it is given as 1 by alpha. So alpha will be 4. So 4 is the answer of this question. Now the next problem type is based on position of bright fringe. So here we have to use n d lambda by d formula. So in YDSC carried out with a light of wavelength 5000 angstrom. Let us say this is in angstrom. The distance between the slits is 0.3 millimeter and the screen is 200 centimeter from the slit. So this is capital D and this is small d. The central maximum is at x equals to 0 centimeter. The value of x for the third maxima. So n will be 3. So 3 times capital D, which is 200 into 10 raised per minus 2 in meters. Lambda is 5 into 10 raised per minus 7 in meters, divided by small d, which is 3 into 10 raised per minus 4 in meters. So 3 will get cancelled out. So this will be 1000 times 10 raised to power minus 9 plus 4, and we have to find answer in millimeters. So that will be minus 5. So 10 into 10 raised to power minus 3 meters. So it will be 10 millimeters. So the answer will be 10. Again, it is based on the position of bright fringe. In YDIC, slits are separated by a gap of 0.5 millimeters. So this is small d, and the screen is placed at a distance of 0.5 meter from them. The distance between the first and the third bright fringe, so first and the third bright fringe, formed when the slits are illuminated by the monochromatic light of 5890 angstrom. So we have given small d, so this is small d and this is capital D, right? So we can say n1 is given as 1, n2 is given as 3, and we have to find the distance between these. So if this is the screen, let us say this is the central maxima. Here we have the third bright, here we have the first bright. So we'll find the position of the third bright from the central maxima, and we'll find the distance of first bright from the central maxima, and the difference of these two will give us the distance between first and the third bright. So we can apply y3 minus y1. So this will be 3 times d lambda by d minus 1 time d lambda by d. So this comes out to be 2 times d lambda by d. Now let us put the values. So 2 times d is 0.5, lambda is given as 5890 into 10 raised to power minus 10 in meters, divided by small d, which is 0.5 into 10 raised to power minus 3. So this 0.5 will get cancelled out. So this will give us 1178 into 10 raised to power minus 7, which is 1178 into 10 raised to power minus 6. So option 2 is the right answer. This answer will be in meters, right? Now the next problem type is based on the position of dark fringe. So here we have to use this formula, which is 2n minus 1 d lambda by 2d. So in YDIC, the two slits are 0.6 millimeter apart. So this is small d. Interference pattern is observed on a screen at a distance 80 centimeter from the slit. This is capital D. The first dark fringe is observed on the screen directly opposite to one of the slits. So the wavelength of the light. So let me just first draw the diagram here. So this is first slit S1, this is second, and we have given that the first dark fringe is formed directly in front of one of the slit. So we can say that is the position of first dark. Okay, now we have to find, and okay, right, so this y, let us, this is y, and which is nothing but half of the distance between the slits. So this will be d by 2. So we know the position of the first bright, first dark. So this should be dark, sorry, not bright. So position of the first dark will be d by 2. So we can say d by 2 is equals to 2 times 1 minus 1 times d is 0.8, lambda we have to calculate, and divided by 2 times small d, which is 0.6 into 10 raised to power minus 3 meters. Now from this, d is also given, so it will be 0.6 square into 10 raised to power minus 6 divided by 2 multiplied with 2 divided by 0.8, so that will be lambda. So 2 will get cancelled out. So this will give us 36 into 10 raised to power minus 8 divided by 0.8. So let me remove this decimal. This becomes plus 1 here. So it will give us 44.5. So 4.5 times 10 raised to power minus 7, and we have to find answer in nanometer. So let us multiply this with 10 raised to power minus 2, divide with 10 raised to power minus 2. So this will be 450 into 10 raised to power minus 9 meters. So answer will be 450. Right, so the next problem type is based on the intensity at a point on the screen in YDSC. So let us see the question. In YDSC, a monochromatic light of wavelength 5000 angstrom is used. The slits are 1 millimeter apart and the screen is placed 1 meter away from the slits. The distance from the center of the screen where the intensity becomes half of the maximum intensity. So here we have to find the position on the slit on the screen where the intensity becomes half of the maximum intensity. And if no information is given about the individual intensities, you can assume intensities are same. So I'm assuming both the sources have intensity I naught. So I1 is equals to I2 and it is equals to I naught. And the maximum intensity will be 4 I naught. And they're saying the intensity is half of the maximum intensity. So that will be half of 4 I naught. So this will be 2 I naught. And we have to find the position. So if this is the setup, here we have intensity 4 I naught. Let us say somewhere here the intensity becomes 2 I naught. Okay. And we have to find this distance y. So what are we going to do? So first you have to find the phase difference at this particular point. Let me call this point as P. So we can use intensity formula, resultant intensity. So it will be 2 I naught will be equals to 4 I naught cos square phi by 2. So this will be 1 by 2, or you can say 1 by root 2 is equals to cos phi by 2. And we know that cos pi by 4 is 1 by root 2. Now from this phi comes out to be pi by 2. Now we know the phase difference. By using phase difference we can find path length difference, because 2 pi by lambda times delta x is phi and phi is given as pi by 2. So delta x comes out to be lambda by 4. So we got the path length difference, and we know that at a particular point P, the path length difference will be d tan theta if both the assumptions are valid. And here both the assumptions are valid because d is very large in comparison to d and lambda is very small in comparison to d. So we can apply delta x as d tan theta, and tan theta can be written as y by capital D, and delta x is lambda by 4. So from this y will be d lambda by 4 small d. Now capital D is given as 1 meter, lambda is given as 5 angstrom, 5000 angstrom, which will be 5 into 10 raised to power minus 7 meters, divided by 4 into D, and D is given as 1 millimeter, so 10 raised to power minus 3. So this comes out to be 1.25 into 10 raised to power minus 4 meters. So we have to find answer in of the order of 10 raised to power minus 6. So that will become 125 into 10 raised to power minus 6 meter. So 125 is the answer of this question. Now let us see another illustration based on the same problem type. In YDIC, light from two identical sources are superimposing on the screen. The path difference between the two lights reaching at a point on the screen is 7 lambda by 4. The ratio of intensity of fringes at this point with respect to the maximum intensity. So here maximum intensity is nothing but 4 times I naught. And we have to find the ratio of intensity at that particular point with respect to the maximum intensity. And we have given path length difference. So from path length difference we can find the phase difference. So phase difference will be 2 pi by lambda times path length difference, which is 7 lambda by 4. So lambda will get cancelled out, so this will be 7 pi by 2. Now we got phase difference. Now we can use intensity, resultant intensity formula, which is IR will be 4 I naught cos square phi by 2, right? And phi by 2 can be written as 7 pi by 4, and 7 pi by 4 can be written as pi plus, or you can say 2 pi minus pi by 4, right? And cos phi by 2 can be written as cos of 2 pi minus pi by 4, which is in the fourth quadrant, and in the fourth quadrant cosine function is positive, so that will be cos of pi by 4. So we can say the resultant intensity will be 4 I naught times cos square pi by 4. So which will be 4 I naught times 1 by 2. So it will be 2 I naught. And we have to find the um, IR with 4 I naught maximum intensity, right? The ratio of the intensity at that particular point with the maximum intensity. So this comes out to be 2 I naught by 4 I naught, which is 1 by 2. So option 1 is the right answer. Now let us see the next problem type, and again it is based on the same problem type. In YDIC, the intensity at a point is 1/4 of the maximum intensity. The minimum distance of the point from the central maxima is, so we have to find answer in micrometer. So resultant intensity at that point is 1/4 of the maximum intensity, which is 4 I naught, which is nothing but I naught. So now what we can do, we can find the phase difference. So we know that resultant intensity is nothing but 4 I naught cos square phi by 2. Now from this we get 1 by 2 or 1 by root 4 is equals to cos phi by 2. So phi comes out to be 1 by 2 will be 60 degrees, so it comes out to be 120 degrees, or right, 120 degrees. Let us keep it as 120 only. The minimum distance of the point, so we have to find the position. So what we can do now, so phi is 120, so let us apply, find the path length difference, right? So what is the path length difference? So 2 pi by lambda times delta x will be equals to phi, and the phi will be 120 times pi by 180, so that will be 2 by 3. So this will cancel out, so delta x comes out to be, pi will also get cancelled out, so delta x will be lambda by 3. Okay, so we got delta x. Now we can use d tan theta formula for the path length difference. So I'm assuming both the assumptions are valid in this case, and it is clearly mentioned lambda is 600, d is 1 millimeter, capital D is 1 meter. So d is very large in comparison to small d, and lambda is very small in comparison to d. So both the assumptions are valid, so we can use this formula. So d y by capital D is equals to lambda by 3, and we have to find y. So d lambda by 3d. So let us put the value. So capital D is 1 meter, lambda is 6 into 10 raised per minus 7, and D is 1 millimeter, so it will be 10 raised per minus 3 in meters. So this comes out to be 2 into 10 raised per minus 4, and we have to find answer in micrometer, so it will be 200 into 10 raised per minus 6 meters, so which is 200 micrometer. So 200 is the answer of this question. Now the next problem type is based on the path length difference for destructive interference. So what happens in this case? For destructive interference, the path length difference is odd multiple of lambda by 2. So it will be 2n minus 1 lambda by 2 for destructive interference. And for constructive, it will be integral multiple of lambda. Right, so let us see the question. In YDIC, the young double slit experiment, the light of wavelength 400 nanometer is used. The dark fringe is obtained at P. So this is point P, and capital D is given as 0.2 meters. The minimum distance between the slits S1 and S2 is, so we have to find answer in millimeters. So what we're going to do, we need to find the path length difference. So this is the, let us say this is the first ray, and this one is the second ray. So the length of this green ray its difference with the length of this black one will give us the path length difference. And by using Pythagorean theorem, we can say this length will be root of d square plus small d square. Even this length is also root of d square plus small d square. And this length is 2d. So the path length difference will be 2 times root d square plus small d square minus 2 times d. And for destructive interference, it should be an odd multiple of lambda by 2. And if you want to find the minimum distance of small d, the right hand side should be minimum. So the minimum value of right hand side will be when n is 1. So we can say for minimum, for d minimum, delta x will be lambda by 2. So we can say root d square plus small d square minus d will be lambda by 4. Now from this, d square plus small d square will be d plus lambda by 4 whole square, which is d square plus lambda by 4 square plus d lambda by 2. Now this d square will get cancelled out, and small d can be written as root of lambda by 4 square plus d lambda by 2. Now if you look at the comparison between these two terms which we are adding, lambda square by 16 is very small in comparison to d lambda by 2. So we can write lambda square by 16 plus d lambda by 2 nearly equals to d lambda by 2. So we can say d is nearly equals to root of d lambda by 2. So which is root of d is 0.2. Lambda is 4 into 10 raised to power minus 7 divided by 2. So this will be 2. So it will be root of 4 into 10 raised to power minus 8. So from this, it will be 2 into 10 raised to power minus 4 meters. And it can be written as 0.2 millimeters. So 0.2 is the answer of this question. Now the next problem type is based on the overlapping of fringes produced by different wavelengths. Now let us see the question. Two wavelengths lambda 1 and lambda 2 are used in YDSC. Lambda 1 is given as 450 nanometer, lambda 2 is 650 nanometer. The minimum order of fringe produced by lambda 2 which overlaps with the fringe produced by lambda 1 is n. The value of n is. So what is actually happening? The position of the maxima which is being produced by lambda 2, it is formed at the same location for the maxima produced by the lambda 1. So if I show the setup, so let us say at distance y, at this location, we can say the n2th order of lambda 2 is coinciding with n1th order of lambda 1, right? And we know what is the position of bright fringe. It will be n times d lambda by d. So we can say y is nothing but n1 times d lambda 1 by d, and it is also equals to n2 times d lambda 2 by d. Now from this equality we can eliminate capital D and small d, and we will get n2 by n1 as lambda 1 by lambda 2. So lambda 1 is given as 450 and lambda nanometer, and lambda 2 is 650. So this comes out to be 9 by 13. Okay, so we can say the 9th order of lambda 2 is coinciding with 13th order of lambda 1. So they are saying the minimum order. So the other possibility will be 18th order of n2 is coinciding with 26th. So the minimum order of lambda 2 which is coinciding with lambda 1 is 9th. So n will be 9. Okay. So now let us see the another problem type based on YDSC. So the shift in the fringe pattern due to insertion of glass slab. So let me first tell you the concept. So if we have a slit S1 and S2, And let us say we have placed a transparent glass slab of thickness T and the refractive index mu in front of one of the slit. Now in this case, the central maxima will shift in the direction of the glass slab. So let us say this is the new position of the central maxima. Now this shift, let me call this as y. Now this shift is given as mu minus 1 capital D by small d times the thickness of the glass slab. So this is the case for a single slab. But suppose if we have multiple slabs, let us say this has a thickness T1, refractive index mu1, it has a thickness T2, refractive index mu2, and the shift is y. So in this case, you can take modulus of mu1 minus 1 times T1 minus mu2 minus 1 times T2 times capital D by small d, right? So these two formulas you have to remember. Now, monochromatic light of wavelength 500 nanometer is used in YDSC. An interference pattern is obtained on the screen when one of the slit is covered with a very thin glass slab of refractive index 1.5. The central maxima is shifted to a position previously occupied by the fourth bright fringe. So it is saying that this particular location is also the location of fourth bright fringe previously. Now the thickness of the glass slab. So we can say y is also equals to 4 times d lambda by d. The thickness of the glass slab we have to calculate. So we have to use this formula. And in this formula, y is given as 4 times d lambda by d. So this will be mu minus 1 capital D t by small d. So so this capital D and small d will get eliminated, and thickness comes out to be 4 lambda upon mu minus 1. So 4 times lambda is given as 500 nanometer, that will be 5 into 10 raised to power minus 7 meters, divided by mu minus 1, so 1.5 minus 1 will be 0.5, so that will give us 10. So it will be 4 into 10 raised to power minus 6 meters, so it will be 4 microns. So 4 is the answer of this question. Now let us see the next question based on the same concept. In YDSC experiment, YDSC performed using a monochromatic light of wavelength lambda. When a glass slab of 1.5 of thickness x lambda, thickness is x lambda, is introduced in the path of the one of the interfering beams, the intensity at the point where the central maxima occurred previously remains unchanged. The value of x will be. So if the intensity is not changing, it means at the central maximum we are also again getting the maxima, but its order it won't be the zeroth order, it will be having some higher order, right? So what we can say, the shift in this case will be integral multiple of fringe width d lambda by d, right? Because we are getting maximum intensity at the central maxima where the central maxima was before. So shift will be n d lambda by d, and this will be equals to mu minus 1 times capital D t by small d. Now from this, d and capital D and small d can be eliminated, and we have to find the value of x, and x is nothing but the factor which is there in the thickness. So we have to find the thickness only. So thickness will be n times, so this d capital D and small d will get cancelled out. So n times lambda divided by mu minus 1. Now this n, okay, so this can written as n times lambda will be lambda is, okay, it is lambda only, right? And thickness is x lambda, okay, right? And okay, let me write thickness as x lambda. So n lambda divided by mu minus 1. So lambda will get eliminated. So x will be n divided by 1.5 minus 1, so which is 2n. Okay. So let us see the possible options. So x can be 2 can be 4, can be 6. So option B is the right answer. Now let us see next question. Again, it is based on the same concept. Wide gas experiment, a thin plate of thickness 10 micron and the refractive index 1.2 is inserted in front of the slit S1. The experiment is conducted in air, refractive index is 1, and using a monochromatic light of 500 nanometer. Due to the insertion of the plate, central maxima is shifted by a distance x beta, where beta naught is the fringe width before the insertion of the plate. The value of x is, so here they have given fringe width shift as x times beta naught, which is d lambda by small d, and this will be mu minus 1 capital D times t divided by small d. Now from this, d capital D and small d will be eliminated and we have to find the value of x. So x will be mu minus 1 and thickness t by lambda. Let us put the value. Mu is 1.2 and the thickness is 10 into 10 raised to power minus 6 and the lambda is given as 500 nanometer, which is 5 into 10 raised to power minus 7. So it will be 0.2 by times 2 times 10. So it comes out to be 4, right? So 4 is the answer of this question. Now it is again based on the same concept, but here we have two slabs. Let us see. So in YDSE, two slits S1 and S2 are D distance apart and the separation between them is capital D. Now if the transparent slab of equal thickness, so both the slab have the same thickness 0.1 millimeter, but the refractive index 1.51 and 1.55 are introduced in the path of the beam of wavelength 4000 angstrom. From S1 and S2, the central bright fringe spot will shift by how many number of fringes? Right, let us say the central bright spot has shifted by n number of fringes, so we can say the shift will be n times d lambda by small d, and we know that the shift is given as, in case of two slits, it will be modulus of mu1 minus 1 times t1 minus mu2 minus 1 times t2 times capital D by small d. Now from this from this capital D and small d can be eliminated and we have to find n. N will be modulus of mu1 minus 1. Mu1 is 1.51 minus 1, t1 is 0.1 into 10 raised to power 3 minus 1.55 minus 1, and I'm taking 0.1 into 10 raised to power minus 3 out, divided by lambda. Lambda is 4 into 10 raised to power minus 7. So this 1 will be eliminated, so it will be 1.51 minus 1.55, so this modulus comes out to be 0.04 times 10 raised to power minus 4 divided by 4 into 10 raised to power minus 7. So this will give us 10 raised to power minus 2. So 10 raised to power 7 minus 6, so that will be 10. So 10 is the answer of this question. So we are done with YDSC problem types. Now let us see diffraction, single slit diffraction. So in single slit, we're going to focus on these 6 problem types. So first is the angular position of the minima, then position of the minima, angular spread of the central maxima, then angular separation of the second minimas, then the width of the central maxima, and then the width of first secondary maxima. Now let us see these problem types one by one. So before that, let me quickly tell you the formulas that we're going to use in single slit diffraction. Suppose if we have a single slit and the light is coming from here and the width of this single slit is A. Now this one is the first minima, this one is the second minima, and this is the first minima below central maxima, and this one is the second minima below central maxima. So if I consider the position of the minima, angular position of the minima with respect to the central maxima, if this is theta, so for minimas, we're going to use a sine theta is equals to m lambda, where m can be 1, 2, 3, right? So for first minima m will be 1, for second minima m will be 2, so on and so forth. And for maximas, the approximate formula will be a sine theta will be m plus 1 by 2 times lambda, where m will be 1 for the first secondary maxima, m will be 2 for the second secondary maxima, right? So this one is the first secondary maxima, this one is the second secondary maxima. And if you want to find the angular spread of the central maxima, so angular spread of central maxima will be given as, it will be 2 theta, right? So that will be 2 times sine inverse of lambda by a. And if you want to find the width, so if you want to find the width of central maxima, so width will be given as, so this width we have to calculate. It is nothing but, if capital D is the distance between the screen and the single slit, then width will be nothing but d times 2 theta, right? And if if the angle is very small, if theta is very small, we can write sine inverse lambda by a nearly as lambda by a. Okay, right. So now let us see different problem types. Now the first problem type is based on the angular position of the minima. Right, so let us see the question. A parallel beam of monochromatic light of wavelength 5000 angstrom is incident normally on a single narrow slit of width 0.001 millimeter. This is small a and this is lambda. The light is focused by the convex lens on the screen placed on its focal plane. The first minima will be formed for an angular diffraction. Oh, so here we have to find the position of the first minima. So we know that theta will be sine inverse lambda by a for the first minima, and lambda is given as 5000. Since lambda by a is very small, theta can be written as lambda by a, right? No, not very small. Let me just put the values. So sine inverse lambda is 5 into 10 raised to power minus 7, and the width of the slit is 1 into 10 raised to power minus 6. Okay, right. They are comparable, right? So it comes out to be sine inverse 1 by 2. Sine inverse 1 by 2 is 30 degrees. So the answer will be 30 degrees. Now the next problem type is based on the position of minima. So let us see the question. So in a single slit diffraction pattern, a light of wavelength 6000 angstrom is used. The distance between the first and the third minima in the diffraction pattern is found to be 3 millimeter. Now this 3 millimeter is very small, so we can say the position of the minimas will also be very small. So we can use the approximation as sine theta lambda by a as simply theta equals to lambda by a. When the screen is 50 centimeter away from the slit, the width of the slit is. So we have to find a. So lambda is given, and 3 millimeter is the distance between the first minima and the third minima. So let me show the screen. Let us, this is the central maxima. this is the first minima, and so somewhere here we have third minima. This angle is theta 1, this angle is theta 2, and this angle is, let us say, theta 2 minus theta 1. Now theta 2 is nothing but sine inverse 3 lambda by a. And since angle is very small, this can be written as 3 lambda by a. Similarly, theta 1 can be written as sine inverse lambda by a, which is nearly equals to lambda by a. So theta 2 minus theta 1 will be 3 lambda by a minus lambda by a. So it will be 2 lambda by a. So we got the angular, you can say the angular spread from first minima to the third minima. Now we can find the distance, the linear distance between these two minima. Let me call this as y. So this will be nothing but d times theta 2 minus theta 1, which will be capital D times 2 lambda by a. So d is given as 50 centimeter, so it will be 0.5 meters times 2, and the lambda is 6 into 10 raised per minus 7, and a we have to calculate. So a and y is given as 3 millimeters, so 3 into 10 raised per minus 3. So 2 times 0.5 will be 1, and this will give us 2. So we can say a will be 2 times 10 raised per minus 4. So 2 is the answer of this question. Now this question is again based on the same problem type. A single slit of width A is illuminated by a monochromatic light of wavelength 600 nanometer. The value of A for which first minima appears at 30 degrees. So we know that theta can be written as sine inverse lambda by A for first minima, and theta is given as 30 degrees. So we can say sine 30 is 1 by 2 is lambda by A. So A will be 2 times lambda, which will be 1200 nanometer, and we have to find answer in micrometer, so it will be 1.2 micrometer. So option 2 is the right answer. Now the next concept or next problem type is based on angular spread of the central maxima. Now the angular spread of central maxima is 2 times sine inverse lambda by A. Let us see the question. A microwave of wavelength 2 centimeter falls normally on a slit of width 4 centimeter. If you look at the wavelength and the width, they are comparable. The angular spread of the central maxima of the diffraction pattern obtained on the screen is 1.5 meters away from the slit will be. So we have to find the angular spread. Let us put the value 2 times sine inverse. This is lambda and this is A. So 2 by 4. So which comes out to be 2 times 30 degrees. So it will be 60 degrees. So option 3 is the right answer. Now the next concept is based on the angular spread separation of two minimas. Let us see the question. A parallel beam of monochromatic light of wavelength 600 nanometer passes through a single slit of width 0.4 millimeter. Angular divergence or angular separation or angular spread, they are synonyms, corresponding to the second order minima would be second order minima. So we can say it will be uh, angular divergence corresponding to the second order minima would be. So it will be 2 times sine inverse 2 lambda by A. So if they are asking about the second minima on either side of the central maxima, right? So let us see the what we are getting from this. So 2 times sine inverse 2 times lambda will be 6 into 10 raised per minus 7 divided by 4 into 10 raised per minus 4. So that will be 2. This will be 3. Can you see the angle is very small, so we can write sine inverse or 2 lambda by as nearly 2 lambda by a. So 2 times 3 into 10 raised to power minus 3, so this will be 6 into 10 raised to power minus 3 radians, right? So the answer will be 6. Now the next problem type is based on the width of central maxima, and we know that the width of the central maxima is 2 sine inverse lambda by a, that is the angular spread, multiplied this with capital D. Now let us see the question. A monochromatic light of wavelength 6000 angstrom is incident on a single slit of width 0.01 millimeter. If the diffraction pattern is formed at the focus of the convex lens of focal length 20 centimeter. So basically the screen is placed at the focal plane. So we can assume capital D as 20 centimeter. The linear width of the central maxima. So let us put the value in this formula. So capital D is 0.2 times 2 times sine inverse lambda by a. Lambda is 6 into 10 raised to power minus 7. A is 1 into 10 raised to power minus 5. Again, theta is very small, so we can say it will be 0.4 times 6 by 100. So that will be 2.4 into 10 raised to power minus 2, or we can say it will be 24 into 10 raised to power minus 3 meters, or 24 millimeters. So option 2 is the right answer. Now it is based on the same concept. So two slits 1 millimeter apart. Okay, now this is based on, okay, right, two slits 1 millimeter apart and the screen is located 1 meter away from the slit. A light of wavelength 500 nanometer is used. The width of each slit is each slit to obtain 10 maximas of double slit pattern within the central maxima of the single slit is dash times 10 raised to power minus 4 meters. So what they are saying, if we have a central maxima, within this central maxima, I'm showing the intensity, right? So on y-axis we have intensity. On so this length will be 2 times d sine inverse lambda by a. So within this width there will be 10 fringes of YDSC. So this width is also equals to 10 times beta. So 10 times beta is equals to 2d sine inverse lambda by a. Now if you compare lambda wavelength and a, so we have to find the slit width and it is of the order of 10 raised to power minus 4. And if you compare this with the wavelength, we can say lambda by a is very small, so the angle will be very small, so this can nearly be equals to 2 times d lambda by a. So and beta is by from YDAC, beta is d lambda by small d, so it will be 2 times d lambda by a. So d lambda will get cancelled out and we have to find a, and a comes out to be d by 5 and d is given as 1 millimeter, so 1 by 5. So we have to find when the central maximum single slit pattern is, so okay, right, so we have to find a. D is given as 1 millimeter, so it should be 0.2 millimeter, or we can write this as 2 into 10 raised to power minus 4 meters. So 2 is the answer of this question. Now let us see the next problem type, and it is based on the width of first secondary maxima. So the diffraction pattern of a light of wavelength 400 nanometer diffracting from a slit of width 0.2 millimeter is focused on a focal plane of a convex lens of focal length 100 centimeter. The width of the first secondary maxima. So what do they mean about that? Width of the first secondary maxima. Let me show the diagram. So this is the single slit and this is the screen. And on the screen, if I show the intensity variation, let us say this is the intensity variation. So basically they are asking about this width. That is the width of first secondary maxima. And how we can find that? And it is also the linear separation between first minima and second minima, right? So what is the, let us say the angular position of second minima is theta 2. So theta 2 can be written as sine inverse 2 lambda by a, and the angular position of first minima can be written as sine inverse lambda by a. If you compare lambda and a, lambda is very small in comparison to a, so we can say this angle will be very small, so theta 2 can be written as nearly equals to 2 lambda by a, and theta 1 can be written as lambda by a. Now the angular spread of first secondary maxima will be theta 2 minus theta 1, so it comes out to be lambda by a. And we have to find the width. Now you have to multiply this angular spread with capital D, you will get the width. So width will be d lambda by a. So d is given as 100 centimeter, which is 1 meter. Lambda is 4 into 10 raised to power minus 7, and a is given as zero point 0.2 into 10 raised to power minus 3. So this will give us 20. So it will be 2 into 10 raised to power minus 3 meters, and we have to find answer in millimeters. So option 1 is the right answer. So we are done with diffraction part. Now let us see the last part, which is the polarization. So we're going to discuss two problem type. One will be based on law of Malus, and the second problem type is based on Brewster's law. Now first let us see these two concepts. So according to law of Malus, if we have, say, an unpolarized light, if you pass this unpolarized light through a polarizer, then the transmitted light will be plane polarized and the intensity will become half. So if this light has an intensity I naught, then this intensity will become I naught by 2. And when we pass this unpolarized light through this analyzer and the angle between the electric field and the pass axis is phi, then the transmitted intensity will be given as I naught by 2 cos square phi, where phi is the angle between the pass axis and the electric field vibration. So this you have to remember. Now Brewster's law, like Brewster studied the polarization in reflection of light. So according to Brewster's law, for any pair of media, there will be an angle of incidence which is known as the polarizing angle. At this angle, the reflected light will be plane polarized and the refracted light will be partially polarized, and the angle between the refracted and the reflected light will be 90 degrees. And tan P is, let's say this medium has a refractive index mu2, this medium has a refractive index mu1, it will be mu2 by mu1. So that is Brewster's law. And suppose if we have an incident light which has no electric field vector, so if no electric field in incident light, then no reflection, only transmission, right? So this you have to remember. Now that is the question based on first problem type, which is law of Malus. When Polaroid sheet is rotated between two crossed Polaroid means the two Polaroid have their pass axis perpendicular to each other, then the transmitted light intensity will be maximum for the rotation of, okay, right. So let me just first draw the diagram. Let me draw it somewhere here. So this is the first one, and let us say this is the last one, last Polaroid, and their pass axes are perpendicular, right? And now we have another Polaroid between these two Polaroid, and let us say initially its path axis was parallel to P1. Now the instant light, suppose we have unpolarized light which is having an intensity I naught. Now here, after the first Polaroid, the intensity will become I naught by 2, and the light will be like this, right? It will be plane polarized. Okay. Now if we rotate, let us say now we have rotated the path axis by an angle theta. Now this angle is theta. So here the intensity will become I naught by 2 cos square theta. Now the angle between the second Polaroid and the third Polaroid is 90 minus theta. So that intensity here after the third Polaroid will be I naught by 2 cos square theta cos square of 90 minus theta, which is sine square theta. So this comes out to be I naught by 8 sine square 2 theta. Now we want this intensity to be maximum. For this to be maximum, this sine 2 theta has to be maximum. So for maximum transmitted intensity, sine 2 theta should be 1, or 2 theta should be equals to pi by 2. So theta should be pi by 4 or 45 degrees. So option 4 is the right answer. Now let us see the next question. A beam of unpolarized light of intensity I naught is passed through the Polaroid A and then through the another Polaroid B, which is oriented so that its principal axis makes an angle of 45 degrees relative to A. The intensity of the emergent light. Okay, let us see. Let me first draw the diagram. So we have given two Polaroid, and let us say the path axis of the first Polaroid is vertical, and the angle between the path axis of the first Polaroid and the second Polaroid is 45 degree. So this angle is 45. Now if we have unpolarized light which is having intensity I naught, then it will become plane polarized and its intensity will become I naught by 2. Now the transmitted light will have intensity I naught by 2 cos square 45 degree according to law of Malus, which is I naught by 4. So option 1 is the right answer. Right, so let us see this question. Unpolarized light of intensity 32 watt per meter square passes through the combination of three Polaroids such that the path axis of the last Polaroid is perpendicular to that of the path axis of the first Polaroid. And if the intensity of the emerging light is 3 watt per meter square, then the angle between the path axis of the first two Polaroid. So again, it is based on, let me show you the question. It is based on this type, right? So where we have two Polaroid which are perpendicular, where path axes are perpendicular, and the angle between the first and the second Polaroid is theta, right? So I can directly use the relation. The transmitted intensity will be I naught by 8 sine square 2 theta, and this transmitted intensity is given as 3 and the incident intensity is 32. So 32 by 8 sine square 2 theta is equals to 3. So this will be 4. So sine 2 theta will be root 3 by 2. So 2 theta will be 30 because sorry 60, because sine inverse root 3 by 2 is 60 degrees. So theta comes out to be 30 degrees, right? So 30 is the answer of this question. Now let us see this question. So we have n polarizing sheets, means n Polaroids or polarizers are arranged such that Each makes a 45-degree angle with the preceding sheet. An unpolarized light of intensity I is incident into this arrangement. The output intensity is found to be I by 64. The value of N will be, okay, right. So if I consider the very first Polaroid or polarizing sheet, which is having a path axis vertical, and we have an unpolarized light, it has an intensity I. So after this, the intensity will become I by 2. Now the next Polaroid has a angle 45 degree with respect to the first Polaroid. So let us say there are n more polarizers in front of the first polarizer. Let us say we have n more polarizing sheet in front of first sheet. Now after transmission by the first sheet, the intensity will become I by 2 times cos square 45 degree. Similarly, after passing through the third sheet, the intensity will become I naught by 2 cos square 45 times cos square 45. So we can say the transmitted intensity will be I by 2 cos square 45 raised to power n, right? And the transmitted intensity is given as I by 64. So I by 64 is equals to I by 2. So and cos square 45 is 1 by 2. So 1 by 2 raised to power n. So this I will get cancelled out. This will give us 32. And 32 is 2 raised to power 5. So 1 upon 2 raised to power 5 is equals to 1 upon 2 raised to power n. So n is equals to 5. So after first polarizing sheet, there are 5 more sheets. So the total number of sheets will be 6. So option 2 is the right answer. Right. So let us say this question. As shown in the figure, three identical Polaroids P1, P2 and P3 are placed one after the another. The path axis of P2 and P3 are inclined at 60 degrees and 90 degree with respect to P1. So it means P1 and P3 are cross polarizing sheet or polarides, and the theta is 60 degree in this case. The intensity of the light at the point O will be, and we have incident unpolarized light. So the source is giving unpolarized light. So I'm assuming it is unpolarized, right? So if it is unpolarized, we can apply this formula. So it will be I naught by 8 sine square 2 theta, and theta is 60 degrees. And this is given as transmitted intensity. So that IIT we have to calculate. I naught is given as 256 divided by 8 sine square 120, and sine 120 is root 3 by 2. So this will be 256 by 8 times 3 by 4. So this will give us 32, and this will give us 8. So this comes out to be 24 watt per square meter. So that is the transmitted intensity. So 24 is the answer of this question. Right, so now let's see another illustration based on law of Millis. An unpolarized light is incident on a polarizer or polarizing experiment, and the intensity of the light beam emerging from the analyzer is measured to be 100 lumen. So when we have given polarizer, analyzer, it means there are two Polaroids, right? And if I show you the situation, so this is, let us say, is the polarizer, which is having a path axis vertical, and then we have a analyzer, which is also having a path axis vertical. Now we have a unpolarized light, and then it becomes polarized, and then we are getting the transmitted intensity, and now this transmitted intensity is given as 100 lumen, right? So this will be 100 lumen. Now what we have done, so we have rotated the path axis of analyzer by 30 degrees. Now this angle is 30 degrees. And we have to find, okay, right. So if this is I naught, this will be I naught by 2. And this is also I naught by 2. So we can say I naught by 2 is 100 lumen. Now if we rotate this, the transmitted intensity will become I naught by 2 cos square 30 degrees, and I naught by 2 is 100 lumen, and cos 30 is root 3 by 2, so that will be 3 by 4. It comes out to be 75 lumen, right? So 75 is the answer of this question. Now the next problem type is based on Brewster's law. Let us see the question. When an unpolarized light is incident at an angle of 60 degree on a transparent medium from air, so light is coming from air to medium, and the angle of incidence is 60 degrees. The reflected ray is completely polarized and the angle of refraction in the medium. So in case when the light is hitting the interface at the polarizing angle, the angle of refraction is 90 minus the polarizing angle, and the polarizing angle is 60 degrees, so 90 minus 60, so that will be 30. So option 1 is the right answer. Now let us see another problem. Light whose electric field vectors are completely removed by using a good Polaroid, allowed to incident on the surface of the prism at Brewster's angle. Choose the most suitable option for the phenomena related to the prism. So I told you, like, when we incident light which is having no electric field, then there will be complete transmission, no reflection. So we can say no reflection, there will be total transmission of the light. So option D is the right answer. Now let us see this question. Unpolarized light is incident on the boundary between the two dielectric media whose dielectric constants are 2.8 and 6.8 respectively, to satisfy the condition so that the reflected and the refracted rays are perpendicular to each other. The angle of incidence should be, right, so this angle should be polarizing angle, right? And they have given dielectric constant, and the refractive index is given as root of epsilon r times mu r, where mu r is the relative permeability and epsilon r is the relative permittivity and or dielectric constant. So we can say for the first medium, refractive index will be root of 2.8, and the refractive index for this, because mu r is given as 1 for both the dielectric media, so mu 2 will be root of 6.8, and we have to find the angle of incidence. So we know that 10 times the polarizing angle will be mu 2 by mu 1. Mu 2 is the refractive index of the medium of refraction, and mu 1 is the refractive index of the medium of incidence. So it is light is incident on the boundary between two media, and to satisfy this condition so that the reflected ray, okay, right. So now let us put the values. It will be root of 6.8 divided by 2.8, so this will be 34 by 14 or 17 by 7. So we can say polarizing angle will be tan inverse 1 plus 10 by 7 raised to power minus or raised to power 1 by 2, right? I can write 17 by 7 as 1 plus 10 by 7. So if you compare this result with the given in the question, theta comes out to be 7. So 7 is the answer of this question. Now let us see one more question based on Brewster's law. If the statement 1, if the Brewster's angle for a light propagating from air to glass is theta b, then the Brewster angle for the light propagating from glass to air is pi by 2 theta b. Let us see. 10 times the polarizing angle will be mu 2 by mu 1, right? And suppose if the light is going from medium 2 to medium 1, then the polarizing angle will be mu 1 by mu 2, which is 1 by tan p, or you can say cot p. So p prime will be pi by 2 minus p. So statement 1 is correct. Statement 2, the Brewster angle for a light propagating from glass to air is tan inverse mu g. That is incorrect. It should be tan inverse of 1 by mu g. So statement 2 is incorrect. So statement 1 is true, but the statement 2 is false. So option 2 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.